In this last example, we are going to graph g of x, which is ln of 3 minus 2x. So recall that ln is log in base e. I'm going to do something I didn't do in the previous example that I maybe should have done, which is actually calculate your domain before doing anything. And the idea is that ln of x, right, this is its graph, and its domain here is all reals, but I meant all positive real numbers. So this is for y equals ln of x. So ln of something needs to be positive. So it's sort of like the square root function, right? Where the domain is everything that's above 0, but 0 included. So the only difference here is that we cannot have 0 since ln of 0 is undefined. So here our domain will be all x values such that what's in the input, so 3 minus 2x, so such that the input is of the function ln is positive. So 3 minus 2x needs to be positive. So simplifying this means 2x is less than 3 or x is less than 3/2. In interval notation, this means we're less than 3/2. 3/2 not included. That gives us our domain. So we should expect when we graph our function, so let's say this is 3/2 here, to have the graph of the function on this side here. It should appear here. So if you have anything on that side, it means we made a mistake, either in calculating the domain or in graphing our function. So they have to reconcile the two. The other thing you want to look at is the vertical asymptote. Okay, and let's look again at the function ln of x. It's found here for ln of x at x equals 0, basically on the y-axis. So the value of the input that makes this part 0. So here, obviously, x equals 0 will be where we find the asymptote. So in our case, it's where this expression is 0 that we'll find our vertical asymptote. So 3 minus 2x needs to be equal to 0. Solving for this, we get that x is 3/2. Typically, the upper bound of your interval in your domain is probably, or lower bound is probably a place where you'll find your vertical asymptote. So we should find a vertical asymptote at x equals 3/2. So here, this is going to be a vertical asymptote for our function. So these features should appear eventually. There's also two things we're going to need in order to graph g that we've seen before, but not so often. Just the following thing. So if you've got a function f of x, okay, and I don't know, maybe its graph is like that, okay. If you're looking at a function g of x, which is f of minus x, okay, so imagine that f of x has a point that's, I don't know, 4, 2, okay. So to get an equivalent, a y value of 2 on the graph of g, what would you need to replace x by? So we've got that here, f of, this means that f of 4 is 2. So I'm going to get 2 out of g if this turns out to be 4, okay? But for this to happen, x needs to be equal to minus 4. So we get that g of minus 4 is f of minus 4, which is f of 4, which is 2. So we see that g of minus 4 now is 2. So this point here will be found on the graph of g over here at minus 4, 2. Similarly, if I have a point that's, I don't know, 5, 3, I would need to have an x value of minus 5 to generate 3 again. So what will happen is that the graph of f will be reflected across the y-axis. So replacing x by minus x reflects it across the y-axis. So this is what happened here. Reflection across the y-axis. So that's one thing. Okay, so we've seen this before. We also saw like functions that have f of x equals f of minus x. Their graphs are symmetrical with respect to the y-axis. For example, the parabola y equals x squared behaves like this. It's symmetrical because f of x is equal to f of minus x. So that was for determining whether a function was odd or even. So when that happens, we have an even function. So all of these concepts have been seen before. There's another one I want to look at, which is when g of x is something like f of, I don't know, 2 times x. So how is the graph of g related to the graph of f? So again, let's take a look at a point like 4, 2 on the graph of f. What would you need to replace x by in order to get 2 out of g? Well, this would need to be 4, wouldn't it? So that means that x is going to be equal to 2. In other words, g of 4 over 2 is going to be f of 2 again. Sorry, f of 4. F of 4, which is going to be 2. Let's take a look at another point. Maybe we can look at 5, 3 also. So if I want the input to be 5 now, x would need to be, so that the output will be 3, right? Because we know that f of 5 is 3. So that would be f of, so what would be the input for g? Well, it would be half of 5, right? Because 5 over 2, maybe I should write it like that. F of 2 times 5 over 2, okay, is going to give us f of 5. So the input for g needs to be half as much as it was for f. So in other words, okay, let's try to look at our points now. The point 4, 2, right, and ends up at 2, 2, right? Because we have g of 2, which is 2. And now we've got g of 5 half, which is 3. So look at how the x value is half of what is used to be for f. See, for f it was 5 and 4. Now it's 5 half and 2. So the graph will just be compressed by a factor of 2. So we'll have 2, 2 here. We'll have 5 half, 3 here. So the graph will be sort of compressed. Okay? So everything will tend to get closer to the y-axis. Okay? All by a factor of 2. So this is what we call the horizontal compression. By a factor of 2. And if it would be, if g of x would be, if we would have g of x, which is f of 1 half of x, everything would be twice as far away from the y-axis. So then it would be a horizontal stretch by a factor of 2. Okay, so we're ready to look at our example. So it's ln of 3 minus 2x. Okay, so let's go back to that. So the idea is that I want to relate g to the toolkit function ln of x. Okay, and how do I want to relate it? I want to rewrite it so that it's of the form f of b x minus h plus k. Notice how I've added the b here. I usually don't put it, but here it's going to be necessary. But a, h, and k do perform the same transformation on g that we've seen already, and now we're adding the b. The b will be responsible for horizontal compression. So I want to write it this way, okay? Now notice that if I expand this, right, it's going to be bx minus bh. So the term including x appears first. And in my function, the term that includes x appears last. So the first thing I'm going to do is switch around my two terms so that x appears first among the two terms. And the other thing is I want to factor whatever coefficient appears in front of x. So that's my next step. So that this is going to be my b. So minus 2x, if I factor minus 2, this is going to become x minus 3/2. To make sure that you did the right thing, just remultiply and you should get back what you have above. So the plus here switches to a minus because I've got another minus here. So minus minus should give me back plus. Okay, so now I'm ready because now it's in the form. F of bx minus h. Now here k and a are well, k is 0 in our case and a is 1. Okay, so we have two parameters h and b that are doing each their own thing on the toolkit function. So this is responsible for, as usual, for a horizontal shift of 3/2. Okay, this guy does two things. There's the 2 and there's the minus. Okay, so this is where what we did before comes into play. The 2 is responsible for a horizontal compression by a factor of 2, and the minus sign is responsible for a reflection across the y-axis. Now, which comes first? Okay, so these two go together, but we do the shift first or the compression first. Let's try both just to see what we need to do. Let's say I shift first. So if I shift first, I'm going to replace x by x minus 3/2. Okay, this is doing the shift. Okay, if I now compress and reflect, okay, what will I do? I need to replace x by minus 2x. Okay, so I need to replace x by minus 2x. This is what I need to do to compress and shift. If I do this, oops, I wrote y twice. If I do this, if I replace x by minus 2x, notice that I won't get what I have above. If I factor the minus 2, I'm going to get x plus 3/2, and I have x minus 3/2. So this isn't right, okay? So I shouldn't be compressing last. I should compress first. So if I compress first, let's take a look that it actually worked. Here, if I compress, I replace x by minus 2x. Okay? And if afterwards I shift, I replace x by x minus 3/2. And now it's correct. Okay? So this is done first. This is done last. Okay, so this part is correct. Okay, all right. So now I know what to do. I take my graph of ln of x, which goes through 1, 0. It's nice to have a point because you're going to keep track of it as you transform your function. So we are going to compress and reflect first. Okay, now the compression will create a graph that's a bit closer to the y-axis. So instead of 1, 0, we're going to have 1/2 0, and it's going to be half as close. So in other words, if I draw a line like this, this new curve should split my line in half. Okay, so this would be y equals ln of 2x. If I reflect it across the y-axis, now it's going to look like this. Okay, notice how my vertical asymptote isn't changing here. So this is my new curve that goes through 1/2, well here minus 1/2 0 because I reflected that point. So this is y equals ln of minus 2x. Okay, And finally, I'm going to shift this graph by 3.5 units to the right. So if I shift my horizontal asymptote, vertical asymptote, which is x equals 0 right now, it's going to become x equals 3.5. Remember that this is what we had calculated at the beginning of the problem. We had calculated the vertical asymptote should be x equals 3.5. If I shift this point by 3.5, it's going to end up at where? Minus 1/2 plus 3.5. That's 2/2, which is 1. So it's and it's going to end up at 1, 0. So our graph is going to look like this. Okay, and then it's going to cross the y-axis somewhere else. So maybe we want to calculate that part as well. But this is our final graph. Minus 2x minus 3.5, okay, which is g. So this is what g is. This is what g looks like. And recall that we had also anticipated, looking at our domain, right, which was from minus infinity to 3.5, that the graph should end up on the left-hand side of the asymptote. And this is what we observe here. So we this is reassuring, right? And maybe I want to calculate finally the x-intercept. So to calculate the x-intercept, you set y to 0 and you try to solve for x. No, that's finding the y-intercept. So x-intercept, it's actually easier. You just replace x by 0. Okay, my bad. So replacing x by 0, that's very easy. You get ln of 3, which is approximately 1.09. So this is 0 ln of 3 here. So that's it. We've got all the features we need for our graph. And with that, you've seen a lot of different parameters that can transform your logarithmic functions in the previous 2 examples.